In the previous class, we looked at what neural nets are and how they work, right? And neural network is a weird model in a sense, right? It's an attempt to model the human brain behavior, really. Okay, so the fact that we as human beings, we have the cognitive capabilities. In other words, we can look at the cat and say, hey, look, this is a cat, right? Somehow our brain makes a distinction. This is a cat and this is a dog. So with the development of neural nets, we became capable of training computers to recognize the difference. One of the most obvious examples probably is Google self-driving car, right? If you think about what the car is doing, really, how do you think it drives itself? What do you think it's using to navigate, to kind of guide? Should it brake, make a right turn, left turn, slow down, accelerate? What do you think it's using?
Computers.
Computers, right. But where does it get the information? Like, for example, let's say it sees the pedestrian and it should stop, right? Where this information is coming from, like pedestrian ahead? Sensors, right? Sensors, cameras. So they have all kinds of sensors surrounding the car. So the car essentially is monitoring the environment, right? And it should be able to capture all the surroundings, and it essentially becomes a picture, right? It takes a picture of the surroundings and should be able to quickly analyze the picture of what's around it and run the image recognition program that says, hey, that thing looks like a tree, that thing looks like another car, and that thing looks like a pedestrian, right? So it should be able to basically behave, have the same cognitive capabilities just like human brain, right? And that is done by the neural net software, essentially. Okay, so in the previous class, we discussed this model, right? We said, and we tried to apply it to the cheese tasting, right? So people taste cheese, and different samples of cheese, they have different content of fat and salt. And we had a very small sample, only 6 observations, right? And we said, well, you know, some of these people dislike and some of them they like, so how about we build a model, right? And I showed you this big fat slide, right, with animation. How basically the neural net is processing the signals that are coming in. So the idea basically is that if we send any signals, so any neural net again should have at least 2 layers, right? It should have, it will always have input layer and the output layer, right? It may or may not have the layers in between, which are called what? Hidden layers, right? Hidden layers basically, their only function is to process information, process signals, right? So what we discussed is, if I send 2 numbers into the neural net, right? Fat content 0.2, 0.9, and these numbers are getting multiplied by the coefficients, right? With the weights that are attached to the arrows, and then added together with the, well, let's call it vertical intercept for the better of lacker term, right? Then that becomes an input into the node number 3. And node number 3 says, let's just transform that input using some function, okay? And we're going to discuss later on what are the 3 most popular functions that are being used by JMP specifically, okay? So in this example, we use logistic function, right? It's called activation function as well. Logistic function is familiar to us from learning what type of model before? Logistic regression, right? So for logistic regression, essentially this z, e to the power minus z. Z is the regression, right? Multiple regression. Intercept plus slope 1 times variable 1, slope 2 times variable 3, blah, 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 right? So we take the multiple regression expression, plug it instead of z, and it gives us an answer. And the answer is between 0 and 1, right? That's how we were able to model binary response, right? Is that cat or no cat, right? Is it, oh, bad example. Will the student remain in the university or will they drop out? Will that employee stay with the company or will they leave, right? That customer will default on the loan or not. Titanic passenger will survive or not. So that's how we were able to map essentially continuous interval from minus to plus infinity only to 0 and 1, right? And that's the idea behind logistic regression, okay? So logistic activation function is just one example. Now let me show you a couple of other examples, okay? Here, let's say I have a very simple neural net that consists only of input layers and the output layer. So just two layers, input and output, nothing in between, no hidden layers, okay? And if I'm using different types of activation function right here, I can get actually the models that we studied already. For example, let's say that my activation function right here in the output node is linear. So this one, right? It says theta 1 plus w1 x1, w2 x2, wk xk. So in other words, that's what it gives me as an output. It's just basically all signals coming together in the output node. It adds them together and spits out the answer. So what does that look like to you? Y equals to theta 1, blah, 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 all that stuff. That looks like our good old friend linear regression, right? Linear regression. So if I'm using the linear activation function, my neural net becomes my good old friend linear regression that we learned, right? What if I use over here the logistic activation function? That's my next slide, actually, okay? So in other words, I do have this theta 1, blah, 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 but I raise e to the power minus that plus 1 and 1 over this sum. That becomes my good old friend logistic regression, right? So I can actually create such configuration of input nodes and output node that I can get back what I learned already. Okay, multiple regression, logistic regression. And then, of course, I can get more complicated things if I start mixing different activation functions, right? They don't have to be the same. I can try a mixture of different activation functions in my hidden layers. I can build more hidden layers, right? In fact, that's what actually complicated neural nets are doing. Now, I don't want to create a false impression that this is how the image recognition works, okay? No, image recognition, like for example, if I want to train the model such that I feed into the model the image file, right, with all with picture of a cat, for example, and I want the computer to run the program, the algorithm, analyze the pixels on this image, and tell me, yeah, it looks like it's a cat, okay? That thing is not enough, right? It cannot be that simple, right? Even that thing, even that thing is not going to be enough, okay? Nobody probably knows for sure, but, well, obviously Google is really good at probably artificial intelligence, right? So they build all these models. So from what I read about Google, artificial intelligence initiatives, the really sophisticated programs that can recognize images, right? That can recognize voice, for example, okay? They include literally millions of hidden layers. So you can imagine that this model is really complicated too. We can't even imagine that, right? Millions of layers of nodes, okay? And each layer, each node in each layer has multiple multiple weights coming into that, right? It has a slope, so each node has a slope, multiple slopes, and the free term, right, intercept. So all of these parameters, like millions and millions of parameters, they have to be optimized, right? The model has to tweak them around to find the best fit for what we're trying to model and predict. So neural nets can become really, really complicated, right? And as we discussed, they're virtually non-interpretable, right? Well, in fact, you know what? Let's give it a spin, okay? Just so that we can see how the program can handle that. All right, so go ahead and go to Scholar. And in the Scholar, in the JMP files, right there, I actually posted the same very example that we kind of looked at, okay? Cheese tasting. 6 samples, 2 of them people don't like, 4 of them people like. Let's see if we can train the model, right? Okay, so go ahead and download the JMP file. So this is not even small data, this is really small data, right? But that's fine. We will be able to still see kind of how this thing works. Okay, so there it is. Okay, so download the file. Should be out there, right? So here's the file. 6 samples. Number 2 and number 3 people dislike. Number 1 4, 5, and 6, they do like. Now, one thing. Pretty much all the models that we did in this class, remember our discussion about how I take the data set and split it into training, validation, and testing, right? Was it a requirement every time when I do the model? No, not really, right? I could use the whole big fat set as my training set. Don't even validate it, right? So use all of my data to build the model, and then after that just cross the fingers and hope for the best. That model does not overfit the data, and if I give it another set, it will perform just as well, right? So technically, I didn't have to do the validation set. It's all supposed to be training, okay? That was totally possible. Well, with neural nets, neural network model does require that we have part of the data to be testing or training set, and another part to be validation set, okay? So let's do the split, right? Let's do it in the same way as we did before. So what I want, 6 observations, not a lot to work with, right? Like every observation counts, so to speak. Right? If I had like 100, then I could say, yeah, it can be 70-30, it can be 25-75, 80-20, not a big deal, right? Here, that's actually a big deal. Okay, so analyze, how do I make the validation column? Predictive modeling, make validation column, right? So let's do this. Out of 6 observations, let's say 2 are going to be my validation set, and 4 are going to be my training set. So I'm going to split it 1/3 versus 2/3, right? So training set supposed to be oh God, what's 2/3? 266, right? 0.66, okay. And my validation set is going to be 0.34, right? 2/3 versus 1/3. And let's do the same thing as we did before. Let's use 100 as the seed value so that we all end up with the same validation and training set, right? So fixed random with the seed of 100, okay? That's what we did before, many times, right? And after that, I'm going to say fixed random, and it creates the column for me. Now, in my case, it picked number 1 and number 4 as validation. What do you have? Same thing? Good. That's what's supposed to happen, right? We'll do the same random seed, therefore it's random, but it's same random for all of us, okay? All right, so now let's train the model and let's see how it does, right? Okay. So I'm going to, well, we never did that before, right? We never built the neural net. Okay, cool. All right, so here, I'm going to go to Analyze Predictive Modeling. Do you see where I should go next? Neural, right? Bam, right there. Okay, so what is my target? Remember we discussed that in the previous class. Neural nets are supervised models, right? Because I'm predicting something with neural network, right? It should be a target variable, target column. What's my target column? Preference, right? People like or don't like the cheese. Based on fat and salt content, right? So these become my X factors, and I will use validation right here. I just put validation column into the validation place, so to speak, okay? And when I click OK, it tells me, hey, you need to specify something else. Look at that. It says you can have, JMP can build up to 2 hidden layers, okay? Can build up to 2 hidden layers. So you can have 1 hidden layer or 2 hidden layers. And there is a note. Second hidden layer is closer to X's in 2-layer model. So if I want layer 1 and layer 2, then second is close to my input, right? Then after second I have first, and after first I have what? Output, right? Output layer. Every neural net has input layer and output layer. The question is how many hidden layers are in between, okay? So second layer is following immediately after the input layer. Okay, and it says, well, in here I have a choice, okay? I can build as complicated model as I want, right? It says you can have 3 types of activation functions. It can be 10H. 10H is something that's called hyperbolic tangent. It's basically the same thing, well, as far as the shape goes. Shape-wise, it's the same thing as logistic regression. It's just more spread. It goes from -1 to +1, not from 0 to 1, like logistic function, okay? So hyperbolic tangent, which is typically what I'm going to use if I'm building the classification model, like in this case. This is a classification problem, right? I want every cheese to be either like or dislike, right? I don't want to predict the cheese density or cheese weight or cheese whatever it is, numerical, right? What I'm trying to do is classify every cheese as yay or nay, right? That's a classification model. So for classification, I'm going to use sigmoid function, right? Can be either logistic, which we don't have this option, or tan h. So tan h is what you need to use when you have a classification, just like here, okay? And it can be linear. Linear is good when I'm predicting what type of response. Categorical or continuous? Continuous, right? Then it is going to become more like my linear regression, right? Okay, or it can be Gaussian. Gaussian, we discussed that. What's Gaussian curve? It's a bell-shaped normal distribution. Remember I told you the story about German mathematician Carl Gauss, who invented normal distribution, and therefore, after, in honor of him, we call normal distribution also Gaussian distribution. So it's a bell-shaped normal curve, okay? So, since this is my classification problem, right? Classifying cheese as like or dislike, I'm going to pick tan h, and 3 means what? 3 means I'm going to have how many nodes? 3 nodes, right? So I'm going to have one hidden layer with 3 nodes. Each node is going to use hyperbolic tangent as my activation function. Okay, simple as that. All right, that's it. Can I put more nodes, by the way? Instead of 3, can I put 5? Sure I can, right? Can I put another hidden layer? Yeah, right? So this is a very flexible model. You see where the flexibility, you can build the neural net in any configuration that you like, really. It's the question of, will it be able to accurately predict what we're looking for? That's all, right? That's all there is to that. Okay, so I'm going to say go, and there it is, okay? That's boring output, right? Just a bunch of numbers. Sucks. Okay, so what am I going to do? Well, first of all, let's take a look at my diagram. It's just a picture. It's just a beautiful picture, but it gives it a little bit of, glare, right? Bam. There it is. Okay, so it says that your input, I sent into the model 2 different variables, right? I sent my x's were salt content and fat content. That became my 2 nodes in what layer? Right here. Input layer, right? I'm predicting preferences, right? Like or dislike. That's my output layer. And I told JMP in the previous window that I want 3 tan h hyperbolic tangent activation function in my hidden layer, right? You see that squiggly sign in every of the node, in every node? That basically says that this is a tan h, right? That's what it looks like, hyperbolic tangent activation function, okay? All right, now let's take a look at, well, first of all, let me ask you this question. How many, I hate to use that word, parameters my model is going to have? How many parameters? Well, each arrow comes with what? Comes with weight, right? Each arrow must have a weight. So I have 1, 2, 3, 1, 2, 3, 1, 2, 3 arrows. So therefore my model will have 9 weights, right? 9 arrows, 9 weights. Also, each node, hidden layer, and my output layer must have also the intercept, right? This theta term. Constant, right? So I have 4 of these nodes. So that's what I'm supposed to have, right? When I'm saying train the model, really what it tells me is what are the weights and what are the constants, right? Okay. I can actually see them. Where do I see them? Right here in my model. Red triangle. Everything in JMP is in red triangle maybe, right? Show estimates. Boom. And that's the funky part. Let's see. I promised you 9 weights and how many intercepts? 4? 4 vertical intercepts, right? So let's see. H11, H11 salt content, H11 intercept. Okay, so what do you think that is? I'm guessing that this is from from this node, fat content, into this node. So this is my first slope, fat content 0.33. This is my second slope for the cell content, and that's the intercept that basically goes right here, right? So the constant at my first node minus 0.24. My second node right here, it has also slope for the fat, slope for the salt, and the intercept. And my third node has this one right here at the bottom, right? It has slope for the salt, slope for the fat. Where is that? Fat and salt and the intercept. And the last four are the intercept and how many slopes do I have. It's how many arrows are coming in, right? So I get input from these three different nodes in the input layer, in the hidden layer, right? So therefore each one should come with a slope, right? So here is my slope 1, slope 2, slope 3, and the intercept. Let me ask you this question. Do you see the same numbers as I do? Nope. So my first slope right there on the top, 0.33. What numbers do you see? Krister, what do you have? 3.0. 3.0. Emily?
I think mine's wrong because it's negative. So.
No, it's not wrong actually.
It's not. Mine's negative too.
Yours is negative too? Some are negative, some are positive, right? The question is, of course, why is that happening, right? Why in the hell is that happening? And that's basically a little bit kind of funky story, right? That is happening because how the procedure starts is first, before it optimizes, before it finds these slopes and intercepts, the program says, let's pick some random numbers, truly random numbers, okay? And these numbers should be close to actually 0. So there is some like boundary, there is some interval where it picks the numbers from. But when I run this program, my numbers, my seed numbers, where the algorithm starts, are picked randomly close to 0. Same applies to you, okay? Your computer picks random small numbers and uses them as the starting values. That's why all of us end up with a different model, okay? So there are like 30 of us here, well, slightly less judging by attendance today, right? But every single one of us will end up with a different model, okay? With slightly different model. They're all going to be close in terms of performance, right? But the specifics, the individual intercepts and the slopes on the arcs, on the arrows, are going to be all different because of randomness, okay? Algorithm says, let's start with random numbers and then let's tweak them around to find the best fit, okay? Now, this is a classification model right here, right? How do we judge the performance of the classification model? Misclassification rate, right? That's the best thing. Okay, do I have my misclassification rate? Yeah, right here. Okay, look at that. This is my, you remember confusion matrix that we did at the beginning of the semester, right? True positive, true negative, false positive, false negative, right? So my confusion matrix, and I remember when we started, we split that thing into the training and validation set, right? Training was 4 observations, validation was 2, right? That's exactly what I see here. That's my training result, that's my validation results, okay? So when I was training the model, what happened is, out of 4 observations, 1 was classified truly, correctly, I mean, as disliked, and it was in fact that the cheese would be disliked, right? 1 was classified as the person will like it, but in actuality it was disliked, right? So the model missed that. And 2 of them out of 4 were classified like, and they were like. So therefore, out of 4 observations, I incorrectly predicted 1, right? Which means right here my misclassification rate is 25%, right? You miss 1 out of 4, that's 25%. Do you have the same results or yours is better? What's your misclassification rate? Same, 25%? Everybody has 25%, right? Amanda? No? What?
Well, I'm just saying 0.
0 misclassification rate. You also have 0, right? 0 means your model is actually good, right? You don't misclassify anything, so... Yeah, R squared, you remember we discussed that. R squared, when it comes to prediction of categorical classification problems, R squared becomes a little bit yucky, right? We don't want to use really R squared. R squared is really good when you have regression, linear regression happening, okay? You're predicting a numerical variable. when you're predicting categories, true, false, default, non-default, R squared becomes very iffy. So therefore, I wouldn't use that as the judgment of how well the model fits. Okay? Misclassification rate is the thing, is the way to go. Okay? But luckily enough, look at that. My validation was 2, and both of them were alike, and I correctly predicted that this is yay. Okay? And that's it. That's basically it. Okay, I told you that neural nets is a black box, right? Signals coming in, signals getting out, and inside of this black box, some weird mixing is happening, right? It's just a bunch of formulas that are hooked up with each other. So you feed signals into one formula, it spits the answer to you, feeds into another formula, right? And these are just all a bunch of interconnected functions, okay, formulas that take input from the previous section, process that, spit it out to the next stage, okay? And this, by the way, is called also forward network. Can you guess why? Because the signal from input layer, they're just being passed forward, right? Sometimes in the brain, what neurophysiologists discovered, sometimes in our brains, the cells, remember I showed you the structure of the cell, right? There are axons, right? Dendrites and axons, right? Sometimes the brain goes into the loop function. So in other words, it can be that one cell is connected, cell 1 is connected with cell 2 with cell 3, and cell 3 goes back and feeds the signal into the cell 1. So in other words, it kind of goes in a circle, right, in the loop. So that would be also the kind of a structure with a feedback, right? So its output is being sent again to be processed as one of the inputs, right? So it's a circular flow of the signal, right? But these are much more complicated things, okay? So, and that's basically all I have to say about neural nets, okay? There is no p-values. There is no testing of significance of the variable, not significance of the variable. These estimates of the slopes and the intercepts, we don't have a nice interpretation to them. So it's really the hardest model to interpret. But as it turns out, also powerful predictor. Okay? Make sense? It shouldn't, well, I mean, it's a simple explanation of what that does, right? But it's really model which is least interpretable. Okay? Other models we can say, yeah, no, odds ratio is 1.3, which means you add one more $1,000s to the salary, there is a 30% chance of person staying, blah, 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 right? So you can do some interpretation of what that model basically shows you. Here, nothing. Okay? Is it high misclassification rate or is it low misclassification rate? That's all. There is nothing else going on, okay? All right, so therefore, from the testing standpoint, what's going to be on the final, that's good, right? There is nothing to interpret. It's a good model. That's all there is to it. Actually, you know what? How much time do we have? 15 more minutes. So there are a couple of things that we can do. Number one, of course, we can stop the class and go enjoy the sun, right? But what I wanted to show you is is this one, okay? Let's do our good old friend Titanic, okay? Completely useless, of course, in business settings, right? But it's a nice example to illustrate, okay? So go to Titanic file from help sample data library, and there you should find the file that's called Titanic. All right. S-T-T as in Titanic, right there. Okay, so that file was fairly straightforward, right? And good thing is we have already training and validation in there, right? Well, let's just try different things, right? Let's just mess around and see what happens. So my target is what? Survive, right? I'm trying to predict which passenger will drown and which will not, right? And that is based on 3 predictors, right? Age, gender, and class on the ship, okay? So let's go ahead and build, let's do stupid thing first, okay? So I'm going to build neural net, right? And predictive modeling, neural. So my survived column is the target. class, age, and sex are the factors, and the validation column goes into the validation. Remember, I told you that neural net, they do require validation, right? Unlike other other models where validation is optional, this one is not. Okay, so we'll click on the OK button, and I'm going to say, instead of hyperbolic tangent, let's use linear.
Will it tell us, like, on the test screens, like, which one to like, use, like, what to put, like, linear, Gaussian?
No, I'll leave it up to you to decide. Use the judgment, right? It's simple. So I'm picking linear right now. Do you think it's going to work out well? Probably not, right? Why? Because linear typically works out well when you have continuous response, right? In this case, I don't have continuous response. It's 0 to 1, right? That's it. So probably linear is not a good idea, but let's just see, right? We're trying things. We can play around, make mistakes, right? There is no harm. Okay, so, and I'm going to have three, in one layer only, three linear functions, 3 nodes, right? So when I click go, here is the result for me, and what do I see? My misclassification rate is 22% on the training set and 21% on the validation set, okay? And by the way, just for the heck of it, let's show the diagram. You see what happened? It's the same structure, really, right? Except in the cheese example, I had 2 inputs, right? Salt and fat. Here I have 3 inputs: class, age, and sex. So therefore, my input layer has 3 nodes, right? Input nodes, number of input nodes is equal to number of your predictors. Simple as that. If I have 50 predictors, there's going to be 50 input nodes, right? Okay, and now the green circles are the nodes in my hidden layer. I said that I want 3, but I picked linear function, right? And the icon on my node shows me that now it's linear, right? When I picked 10H, it was like squiggly line, right? Flattened S. That's basically the icon form can tell you which function did you use, right? So I have to remember that. Where's my misclassification rate? 22%.4 and 21.2, right? Okay, let me just run a different model, right? I'm trying to build a good model, and I'm trying to see what works and what doesn't. So let's do it again. I'm going to go predictive model, modeling neural. Same thing, so I can just press recall, right? Click OK, but this time around I'm going to, instead of, again, 10H, I'm going to use 3 Gaussian functions, right? I don't even know how it's going to work, quite honestly, because Gaussian implies that you have continuous variable distribution, and all of my predictors are not continuous, right? So it's going to be weird. Okay, anyhow, same configuration. What I'm doing is I'm changing the type of activation function, right? Type of transformation that my formulas do. So I click OK, and what does that tell me? It tells me that, oh, and again, by the way, if I look at the diagram, look at that, same configuration, right? But now I have this bell shape, right? It shows me the type of an icon. It shows me what type of variable or what type of transformation, activation function I used in each of the nodes, right? And how am I doing in terms of performance? Is it better or is it worse? Slightly better, right? Because I used to have like 21, 22% misclassification. Now it's down by approximately 1%. So slightly better, not terribly great performance, right? Well, let's see how my best candidate would be what? 10H, right? Because 10H is 0-1 type of response, and that's exactly what I have. Let's hope that it will work out. Okay, here is my data set. So let's go back to analyze, predictive modeling, neural net, and recall, so that I have the same setup. Click OK, and I'm going to leave things just the way they are, right? 3 hyperbolic tangent functions in one hidden layer, and click on the Go button. 21%, 20.5%. So is that a drastic difference? No, not really, right? So in this case, which was the best? That was my Gaussian, right? Gaussian gives me On the validation, it gives me 21.2%, right? And the last one, this one right here, no. The 10H, right, hyperbolic tangent, gave me 20.5. So it is slightly better, right? Not a stellar performance. Still, if I pick any of these models, I'm misclassifying anywhere between 20 to 22%, right? So the difference aren't that significant, quite honestly, right? Well, you know what? Let's do one last thing, right? What if I'm going to make things even more complicated? What if I add the second layer, second hidden layer? Will that improve the performance? Let's see, analyze, again, predictive modeling, neural net, and I'm going to hit recall, and I click OK. And now I'm going to use 3 hyperbolic tangent in layer 1 and 3 hyperbolic tangent in layer 2. Okay, so I'm building bigger neural net. And let's click on the Go button. So first things first, performance, 20.5 misclassification rate. Is that better? Nah, not really, right? That didn't help. But it sure enough created, of course, more complicated structure, right? So here's my layer 1, here's my layer 2. And of course I have more parameters, right? Because it has more arrows connecting the nodes. So therefore there are more slopes, there are more intercepts. So it's a more complicated thing to optimize in the first place, right? But that's the idea behind the neural net, okay? Any questions?
Like this diagram, what is this showing us specifically? What's the
Oh, the diagram?
Yeah.
Diagram is just kind of to look at that and say, oh my god, it's so pretty, cool thing.
What's
Nothing.
the practical application of this?
Of this model or of the diagram?
Of this model system, or yeah, of neural networks.
Oh, practical applications are huge. Voice recognition, image recognition, handwriting recognition, predicting. It's really here, right? Let me show you. Okay, hold on. Let me open this file that we had recently, right? Matrix. These are everything. These are all the tools that we have learned during this semester, right? So look at that. Classification tree is used when your target is categorical only, right? And responses and predictors can be categorical or continuous. Multiple regression is used only when your target is continuous, right? A neural net covers all the grounds, all types of targets and all types of predictors, right? Can be continuous or categorical, covers them all. Okay? So artificial intelligence, there are multiple applications. Image recognition is one thing that comes to mind, right? It can, like, companies are trying to optimize amazing things. Like, for example, I can post that actually there was a paper recently in Wall Street Journal, prices at gas stations. So when do you charge higher price, when do you charge lower price? Can track the demand. So basically when the demand is high, you want to charge higher price, right? When the demand is low, to encourage people to come to your gas station, you can charge lower price, right? So it can basically track the history of purchases, traffic, and judge, basically build a model in order to predict how you should adjust the prices up or down, okay? You can predict, for example, insurance, right? Insurance is one of the industries is going to get helped by data analytics. Like, for example, the biggest question that insurance companies have, how much money to charge as the insurance premium, obviously, right? And what do they use? They use, what kind of information do they use to determine how much you're going to pay monthly? Credit score. Did I tell you the story about the credit score thing? Yeah. At one point, I asked for the quote. You know, insurance is fun business, right? You call them and say, hey, can I have a quote? And they go through the same questions, right? Where do you live? Do you rent or do you own? Blah, blah, blah. So some questions that they were asking is, what's your highest degree? Bachelor, master, or PhD? And we need to run the credit score on you. I'm like, what in the sweet hell my credit score has anything to do with how I drive. But apparently it does. So they ran the model, right? And the credit score turned out to be a statistically significant variable with p-value less than 0.05. That's basically the statistical explanation, right? But the actual, well, nobody knows why it matters, right? The explanation that they basically came up with is like how you drive if you take, risky moves, right? This, chess pattern, right? So you just change the lanes trying to get 2 car lengths ahead of you, right? So if you take these kind of risks, that may be reflected in your credit history as well, right? So if you were late on some payments or declared bankruptcies, that can also tell us that you're a risky person, which means that you may be driving more dangerously, and therefore you're more likely to get into the accident, right? So you can run neural network model to try and predict how much to charge, for the insurance, right? Like people who are at high risks, you want higher premiums, right? Then another kind of fun example that I recently bumped into is oil trading. Okay. Oh, and another one is from agriculture. Let me tell you this one. Okay. Apparently, the manufacturers of the agricultural equipment, such as tractors and like seeders, right? So, in order to plant the corn or the wheat, nobody like going on the field and just throwing the handfuls of seeds, right, anymore. So it's basically like the tractor goes through the field, right, and they lift the upper layer, right, and distribute the seeds. So there are companies that use data analytics in order to predict based on temperature, based on like typical, for example, precipitation profile of the place, right? Based on like chemical analysis of the soil, how densely to distribute the seeds and how deep to plant them in order to gain the best results in terms of the yield per square foot, for example, from the field. So therefore, companies like John Deere that manufacture agricultural equipment, they're buying the software and they are putting the software into the computers that are running on the tractor, right? In order to adjust dynamically how deep you plant your seeds and how densely you spread them, etc., etc. Okay. Another application, cool application that I read about was oil industry right now. Right now, what happens with oil prices? Let me ask you this question. Oil prices are going up, okay, for no good reason. Well, there is a good reason. It's called greed. That's all there is to it, okay? So oil futures are going up because more banks are investing into oil futures. And it all rides on really BS assumption that the world is going to consume more oil and we're going to have a shortage of oil because of, Keystone pipeline experienced an outage and there are tensions in the Middle East and, Russia is pumping more oil, or less oil, so some stupid crap going around basically. And recently there was a paper, an article in, I believe, Wall Street Journal. Basically, it looks like the Saudi Arabia, who reports lower levels of the oil, may be lying. And there may be actually high levels of oil reserves, in spite of what they're saying. Okay, how did they find it out? Easy. Well, not so easy actually. They analyze satellite images from tankers. So what happens is, what happens with oil, like they can extract the oil from under the ground, but they don't want to sell it yet, creating artificial shortage on the market, so they put it on the tanker and put the tanker in the sea. So it's not going anywhere, it's just like a pot full of oil sitting, floating on in the ocean. Okay, so it's like a floating storage of oil. And what they did basically is they took the satellite images of these oil tankers, right? And when you look up, like from the space down on the tanker, there is like, you can see the sun elevation, right? And you can see how high is how long is the shadow from the brim of the tank on the surface of the oil. And by a length of this shadow, you can judge kind of the level of oil, right? High or low. So they use satellite images to estimate how much oil is floating in the tankers out there in the sea and estimate the actual reserves of oil. So all kinds of crazy applications out there, okay? Not to mention the self-driving cars, obviously, right? Self-driving cars run exclusively on neural network, okay? Hand recognition, handwriting recognition, speech recognition, image recognition for the medical applications, right? Then future applications in medicine can actually include something else. Like how do you diagnose what's going to help, right? So the patient comes to you with weird symptoms and you don't know what to do. Happens all the time. So regular doctor, he knows just 1, 2, 3, 4, 5 things, right? They test your, I don't know, thyroid, testosterone, then cortisol, maybe something like. They're all in range. They say, yep, you're fine. Go home. You know, take a hike. It's all in your head. So we don't know anything about that. Well, in actuality, what you can do is you can run complete profile on the patient that includes full panel of blood work, right? Mineral, for example, how they're doing on magnesium, iron, you know, copper, zinc, vitamin B, vitamin B9, B12, B5, B6, vitamin D, vitamin A. Then the full profile, like you can run genetic testing on the person, right? And then it all converges together, and we have a bunch of patients' information, right? What helped in each individual case. So you can run really big comprehensive model like that and say, hey, you know, if patient comes in and they have elevated magnesium, they have, you know, low cortisol, and they're low on vitamin D. Bam, the model, you know, runs, and then it says, yep, he has this condition, so they need to take more zinc, they need to take more vitamin C, they need to take less carbohydrates, more protein, etc., okay? So make the diagnosis and treatment much more manageable and data-oriented as opposed to what the doctor remembers from medical school, okay? So huge applications. All right, I feel that we ran over. Okay, so let's stop.